Okay, let's discuss the overview of the MTH movement 4. So we have a differential equation. So if we have a differential equation, that means we have a relation between dependent variable and their derivatives. So, so if we have more than one independent variable, then we have the ODEs, basically ordinary differential equations. If we have more than one uh, independent variable, let's say x and t, then we have PDs, the partial differential equations. So, if the problem, the differential equation is assigned with the initial condition, that means we have the condition given on initial point, the starting point, that is called initial value problems. If we have the boundary conditions, then it is called boundary value problem. That means the condition is defined on the end point interval. So in this course, PD is not there, so we focus on the ODs. So in OD, so if we have one dependent variable, that means let's say y of x, then we have simple OD. If we have more than one dependent variable, let's say yx and y and z, then we have a system of OD. So if you have more than 2, 3 or n, then we can have a system. So in this course, the system is also not discussed in detail. So we will focus on the one independent variable, one dependent variable. For example, the first order OD is given here. So in next we have this linear or non-linear. So linear or non-linear. So in non-linear we have non-linearity in the dependent variable. Linear is basically when we have the power of a dependent variable and their derivatives are basically 1 and they don't have any multiplication on. We have simple definition also. So we focus in the course that is the linear one. So in non-linear one, the simple one example. So in non-linear we have only special case so that we can solve it. But we are not going to solve in detail the non-linear problems. So in linear, so before solving to it, we discuss the Picard's axial ingress theorem. So it basically tells us that whether there is a solution or not for the given problem. That means we are going to solve it. So beforehand, we want to know whether we are going to solve it or not. If we are going to solve it, there is a solution or not. So for this, we know that Picard's axial ingress theorem will let us know there exists a solution and there exists a solution if it is unique or not. So now let's focus on the course part, that is the linear, and then we have this first order and the higher order. If we have the first order differential equation, that is ordinary differential equation, then we have different cases to solve it. And to solve it, we have different techniques. So in techniques, we have direct method, iterative method, series. So direct method, so basically we get the exact solution of the problem. So in which we have method of variation, method of underdetermined coefficients, and even the Laplace transform is also one of the case. For the higher order ODE, if you have the first order ODE, we have different cases. So we can solve, for example, separable form, linear, and check. In iterative method, we go to the approximate solution, not the exact. So in which we have this Picard's approximation method, we have Euler method, we have improved Euler method. And in series solution, so basically direct method is only for a restricted class. We have a special cases where we can directly solve it, and to solve it in more general, we have then iterative methods, we get the approximate solution, and in some basically we can also find out the series solution. In the series solution, we have this power series method and the Frobenius method. Power series method, when we have regular point, and then if you have this Frobenius, that means if you have the regular single point. So now let's try to come to the. We have this first order ODE and the higher order ODE. In the first order ODE, we have different cases. The first one is if we have the separable form, then we can solve it. If not, then we will reduce it and then solve it. In the reduce it, that means if we have some, let's say, homogeneous type of form, then we can convert into the separable form and then solve it. If we have the exact form, then we can solve it. If not, then we reduce it by using the integrative factor. If we have the linear form, we can solve it by using the integrative factor. If not, then we can basically reduce it. And in this case, we have only one non-linear problem called Bernoulli problem. It means we can use the transformation, convert it to the linear form, and then solve it for the first order case. And for the higher order case, we have two situations. One is homogeneous, one is non-homogeneous. So in homogeneous, we need to have the only the character equations, and in non-homogeneous equation, we have to find out the character equation plus the particular integral. So then we have two cases. One is the variable coefficients, higher order linear differential equation. One is constant coefficients. So in variable coefficients, we have this special name called Cauchy-Euler. That means using this, using some transformation, we basically convert it to the constant coefficient and then solve it. Or if we have some special variable coefficients problem, then we can even solve it, but not all the problems. And in constant coefficients, we have this method different to find out the PI, particular given method of variation of parameter, method of undetermined coefficients. And method of undetermined coefficients is only to solve. We have some special right hand side. One is let's say x or a polynomial type, or e to the power x or sin x or cos x or their multiplication, not for all the problems. So it is for this very special class. And then we can also try to solve the method of variation parameter for the constant coefficients. Also, the Laplace transform is also for the constant coefficients. So these are the general idea to solve it, and then let's basically I will try to upload the solutions, assignment solution in the description. You can download it.